All right, so thanks for the opportunity to come and talk to you guys today. This work was funded through the Australian Climate Service, and I've acknowledged a whole bunch of co-authors on here. This paper is now published in JSHES under that same name, and it's not specifically about Earth system modeling or coupled modeling, but I thought it would still be relevant to this group because it's really about uncertainty and projections and the relationship to model-to-model uncertainty. Particularly in CMIP, the coupled model intercomparison project. Okay, so um, just start off by acknowledging this very long list of co-authors. This was co-led by Michael Gross, and this big group of people who mostly work on downscale climate projections to produce high quality climate projections information to serve the public. So yeah, this work this study is only possible because of their work. I'm trying to get my slides to move. Okay. Excuse me. So there's more climate change projections data now than ever before. And we have this abundance of high quality, high resolution climate change projections too, ready to be used in applications and now available to users through multiple sources. And, those include global models, regional models, bias correction methods, and lots of different methods to estimate hazards and other impact indices. And the question is, how should users make sense of all of this information? So I'll talk a little bit about our investigation of region average temperature and rainfall changes. And I'll start by just discussing the data that we used in this study. So we used 35 GCMs and 4 RCMs um, and 3 scenarios. So the data was taken from the historical SSP 126 and SSP 370 scenarios. And we used 2 large ensembles as well to look at the spread within ensemble variability and changes in variability. So note that NARCLIM and the Queensland Future Climate datasets also have other scenarios. They've also got the SSP 245 scenario, and there are convection permitting simulations also available for some of these RCMs, but we don't analyze any of that in this study. So primarily here we're focused on mean changes and interannual variability changes. And we note that here that some of the results that I'm presenting might be different if you were to look at extremes. So just a quick visual to show you the NRM regions and natural resource management regions that we do our analysis over. So we looked at area average quantities for these 4 large regions. And so I'll just leap straight into it. So I guess the central question that we're addressing here is what explains variations in regional projections. This is Australian average temperature on the top and rainfall on the bottom. And I'm just showing a line here for every model simulation that we analyzed. So, lumped into these plots, we have GCMs and RCMs, all area averaged for the country. So the first point to know is that, temperature under all these scenarios that we looked at essentially goes up in the future. And those temperature changes are very largely explainable by looking at the scenario that they were taken from. So that's that top row there. And on the bottom row there, you can see for rainfall that the spread is in both directions from the present day. And you can see that SSPs, the forcing scenarios, don't stratify rainfall projections much at all. The third column that I've added here, this shows you the projections by the end of the century, separated by model ensemble. So the first row there's the GCM ensemble, and then after that, each box after that is the RCM downscale projections. Excuse me. And you can see here that by and large for temperature, you get a similar range from any ensemble that you decide to use, as long as you've sampled the same scenarios. But on the bottom there for rainfall, you can actually see that there's quite a bit of variation between the ensembles. So that's something important to note for users when you are providing climate change projections. And here, this fourth column, we look at this by separating it by GCM or driving GCM. So it's a bit of a strange plot. I've lumped in here GCMs and RCMs together, but the point of this is that the sampling of GCMs is apparently very important, especially for rainfall, less so for temperature, but especially so for rainfall. So let's take a closer look at that. So here you can see each one of these gray bars is the range and projections across scenarios for a single GCM or driving GCM. So for example, if a run was taken from NARCLIM, we assign it here to the box of its driving GCM. And you can see here this seems to create a very large spread in models. So users need to be very considerate about the sampling of GCM changes. This figure here shows the late 21st century change for different scenarios and model ensembles again. On the left is the scenarios for GCMs, the middle is for SSP126, and the right is for SSP370. And you can see that the ensemble names are marked there on the bottom. Light green is the GCM range for that ensemble, and dark green is the actual RCM projection. So here we're into comparing the uncertainty due to regional climate models versus their driving GCMs. That's what these two different shades of green show you. And the red dots here are the models that are higher climate sensitivity. So what we've done is we've separated them out from their ensemble for their ensemble spread. And you can see that higher climate sensitivity models have higher Australian temperature change, regardless of which scenario you're looking at. But once you've separated out high climate sensitivity models, the ensembles start to look very similar otherwise. So um, this question about how we should treat hot models is a really important one, but we note here the implications for users. We don't provide an opinion or a solution on what to do about this, but just to note that the ensembles are similar when you take into account the hot model problem and the sampling of hot models. Okay, so how different are these model ensembles when it comes to precipitation? This is the region average scale now. So the four columns are the four regions, and the two rows are the two seasons, DJF and JJA. And each colored bar is a different model ensemble. So the rows are seasons and columns are regions, and we can see that there's some really interesting similarities and differences. And we'll just obviously hard for you to see this just staring at these messy box plots, but bar graphs. But let's have a look at two specific examples right now. So first we'll look at rangelands. This is the biggest region of Australia. That's the orange region in the middle, and it covers much of the interior of the continent. Looking at this is the projections of summer rainfall under a high emission scenario, we can see that a very wide range of futures is plausible. However, if we just looked at only one RCM ensemble, we might draw very different conclusions depending on which ensemble is chosen. So since we consider all of these models to be plausible, users should be aware that sampling a wide range of models will more adequately sample uncertainty. And I guess for interest for this group, this ESM working group, that black bar on the left is the GCMs from CMIP 6. And you can see there's very large model uncertainty for this region. If I showed you Northern Australia, it was about the same. Here's another example. This is winter rainfall change for Southern Australia. And here we see a lot more consistency. So reductions in rainfall with global warming are projected by pretty much all ensembles. Along with physical understanding, this should give users more confidence in the projected change. Choice of the model ensemble here seems to be less critical for users. So again, for interest for this group, you see that there seems to be some consistency amongst GCMs around the projections for Southern Australia.
Do you mind if I ask a question while you're going, Sugata?
Sorry?
Do you mind if I ask a question while you're going?
Please go ahead. Yeah, it's weird talking to a screen.
Yeah. So if you go back one,
Yep.
do you know what this plot would look like if you did it separately for Southwest and Southeast? Because
Yes,
we know that winter rainfall in the Southwest is an observable trend that the models agree on, but previously I've always understood that the Southeast is quite different.
Yeah, so this is the long-term projected change under a high emission scenario, and I think there is some consistency around winter drying in the future in the southeast as well. I don't have the numbers to show you right now, but I think that is a fairly consistent projection. The uncertainty for Southeast Australia comes in when you look at the annual rainfall, because the summer rainfall is highly uncertain in the projected change for Southeast Australia. So yeah,
Cool. Thanks.
but I think this one result is probably somewhat consistent. So if you separate by processes, by time of year, and that kind of thing for drivers of change, maybe there's a bit more confidence in this aspect than there is about summer rain. Yeah. Okay, so how do the RCMs change the GCM projections? So maybe that's not of huge interest to this group, but I'll just talk through this anyway because I think it's important. Because at the end of the day, what people often make decisions on is the downscale projections rather than the GCM projections themselves. And I think this is actually kind of interesting and important, that these regional models, they're forced at their boundaries with GCM model outputs. And so I guess the question is, do regional models affect the GCM projections of rainfall? And in this plot, this is the ACCESS ESM 1.5 GCM projection in the top row. And every RCM's projection is shown below as a difference to that top row. So you can see a range of reds and blues showing where regional models vary the GCM projection in different ways. And I'm just going to show a sort of zoomed in look at a couple of particular cases. I'm not going to talk about which models these are and that sort of thing, but just as an example, here are two RCMs for the change in rainfall of the same season. And you can see the magenta contours are locations here where the RCM projection is actually of opposite sign to the GCM itself. So changes to the projected signal can be quite significant at times, and it's not clear why this happens in these models, and further understanding these processes I think would be very useful. So, I mean, of course, we do expect RCMs to modify GCM projections at fine scales. That's somewhat the point of regional modeling. But should RCMs change the GCM signal even at relatively large scales? I think that's a question mark and a contentious issue. And one potential reason that they might is because they are apparently better able to resolve processes associated with coastlines and steep orography. So this plot is rainfall change for GCMs on the top and RCMs in each row below. And in the magenta box here, I've highlighted the downscaling of one global model where the projections are broadly similar over Southeast Australia and where orography and coasts dominate in the landscape. Again, this is now annual changes. So this is not winter rainfall change, this is annual changes. In the orange box here, I show a counterexample where model projections differ quite significantly between the downscaling simulations. So if you stare at this sort of plot long enough, you're going to see that there's lots of interesting detail and that deserves greater investigation. But there's these cases of consistency and lack of consistency that I think are very poorly understood by the providers of climate change information to users. Okay, so now let's turn our attention to change to variability and changes in variability. I'm just going to focus on rainfall. So these heat maps show the late 21st century change in standard deviation of seasonal average rainfall, again in the NRM regions, that's the columns. And you can, it's often stated that variability is broadly projected to increase with global warming. However, this is actually not really universally true at the regional scale for Australia. And you can see that with both at these regional scales, you can see both increases and decreases found in both the regional models and the which is the row on the bottom, and the global models, which is the row on the top. Okay, and looking at the same quantity for a large ensemble, here, I've shown the EC3 large ensemble. Looking at the same quantity for a large ensemble, we can see large variations in the projected changes for winter, even within one global model, although this differs by season and region. Okay, so there's been a quick presentation. I hope it's been useful. Here's my summary points. I guess some of the key takeaways here is that, CMIP is a very important and large undertaking, and actually it determines the vast majority of uncertainty aside from scenarios, especially for rainfall. The model-to-model differences are really, really important, and constraining projected changes in the future is really going to be largely about constraining, I think, that model-to-model difference rather than focusing simply on internal variability or focusing on scenario differences, at least for rainfall at the regional scale. And changes made by RCMs to GCMs are often significant, but not systematic. And I think that's another thing that's really concerning that deserves a lot more attention than it currently gets. And I touched briefly on interannual variability of rainfall changes. And I guess the key point of that is that there's no consistency on even the direction of change of variability. And if you want to read more about this topic, you can look at our paper in JSHESH. It's now publicly available.